Hi, I'm Zhizhen, a PhD student at UC San Diego. Today, I present our work on quantifying safety of learning-based self-driving control using almost barrier functions. This is a joint work with Professor Tsui-Wei Weng and Professor Sicun. Recently, neural controllers have shown great promises in performance. However, they are represented by neural networks, and neural networks are known to be highly nonlinear and complex. Thus, they are hard to analyze. In this work, we propose neural almost barrier function to analyze the behavior of the neural controller. We demonstrate the end-to-end pipeline to train the neural almost barrier function and certify the barrier functions. We demonstrate the effectiveness of the procedure in 3 simulation environments. First, let's define some terms. Given a scalar function b and a system f, the lead derivative LF of b is defined as follows. It measures the rate of change of b over time along the direction of the system dynamics. Let's then define barrier functions. Barrier functions have 3 properties. In safe regions, it outputs positive values. In unsafe regions, it outputs negative values. As boundary, the lead derivatives are positive, which pushes the vehicle back to the safe region. Barrier functions forms an invariant set around the safe region. We extend the concept and define almost barrier function. In almost barrier function, a small leaky area on the boundary is allowed. In these areas, we allow non-positive lead derivatives. We can understand these areas as where unsafe behaviors may happen and operations should be avoided. Next, we introduce the procedure of the training and certification process. This flowchart shows the entire pipeline, and I will walk it through piece by piece. First, we need to collect data to train the barrier function. The data includes safe and unsafe samples. To collect safe data, we run the trained neural controller and label the visited states as safe samples. We then use k-nearest neighbor technique to randomly generate unsafe samples that are far from the safe region and label them as unsafe data. With safe and unsafe data collected, we can train the neural barrier function. This is the loss function for training the barrier function. The loss function consists of 3 parts. The first term regulates positive outputs for safe samples. The second term regulates negative outputs for unsafe samples. The third term requires positive lead derivatives around the boundary. Next, let's talk about the procedure for certifying the trained barrier function. Let's work with an example state space shown on the right. We first grade the entire state space into small cells. Safe cells are the cells where all states in the cell have positive barrier function values. To ensure this, we need to check whether the minimum function output of all states in the cell is positive. To do so, we utilize the Cron algorithm for neural network verification. Given an input box and a neural network, Cron finds the overall approximation of the lower and upper bounds on the outputs. Since our barrier function is a neural network, we use Cron to find the output bounds for each cell, and the safe cells have lower bounds greater than 0. Similarly, we can find unsafe cells whose output bounds are smaller than 0. Other cells are categorized as boundary cells. For these cells, we want to certify that their lead derivatives are greater than 0. To do so, let's bring back the formulas of lead derivatives. To bound the lead derivatives, we need to compute the upper and lower bounds of the derivative of the neural barrier function and of the system dynamics. For the barrier function derivative, we can use Cron-like idea to compute the bounds. For the system dynamics, we can use sampling-based approach to estimate the Jacobian in the local neighborhood. Both bounds are over approximations. The details can be found in our paper. We can categorize all cells into certified cells and uncertified cells. Certified cells have lead derivative lower bounds greater than 0. Thus, we can establish almost barrier function, which is a barrier function with a small proportion of uncertified cells. Next, let's talk about experiments. We demonstrate results in 3 environments: kinematic vehicle model, dynamic vehicle model, and torque racing environment. The dynamic vehicle model includes lateral slips. If the vehicle tries to turn hard under high speed, it will slide to the side. The torques environment is a high fidelity racing simulator and removes the ability of resetting to arbitrary states. In the dynamic model and torques environment, we trained barrier under partial observability, and the details can be found in the paper. This figures shows the trained barrier in 3 environments. In kinematic model, the barrier is trained in 3 dimensions and represented as the ball. For dynamic and torques environment, the barrier is trained in 2 dimensions and drawn in the XY plane. The surface plot shows the value of the barrier function. In these figures, we compare the performance of different controllers for path tracking tasks. The left figure shows the trajectory of the controllers, and the right figure projects these trajectories into barrier landscape. The trajectory of the newer controller is always contained inside of the barrier function, and the Stanley and MPC controller usually leads the vehicle outside of the barrier. In this slide, we demonstrate some applications of the trained almost barrier function. We can conduct backward reachability analysis on the trained barrier to construct a safety monitor. A human operator could take over at early stage if the vehicle is approaching the unverified region. Barrier functions could also optimize controller by adding the samples around the unverified region into the controller training. In the right figure, we can see the performance improves after new samples are added to the training. In summary, we provide the complete end-to-end procedure of training and verifying barrier function for newer controllers. We demonstrate the results in 3 simulation environments with increasing difficulties. We also provided possible application of the procedure. With that, my talk is concluded. Thank you.